Hello, and welcome to Patch Math, where today we are going to patch your math knowledge in using linear systems to solve word problems. All right, take a moment and pause this video to read this word problem. This is a very common format that you will see, and the reason I wanted to go over this word problem is it is a comma away from being clear. And let me explain what I mean by that. First off, it's important that we recognize what we're trying to solve for, and we are trying to solve for the number of students in each van and bus. That's our unknown. So we're going to come up with our let statement, and we're going to say, let, I know that when you're doing linear systems, you usually use X and Y. So I'm going to use that here. If you want to use other variables like V and B for van and bus, you're more than welcome to. So I'm going to X equal the number of students in the van, in each van, and I'm going to Y equal the number of students in each bus. Now that you got your let statement, we can start piecing it together with little piecing. We can start piecing this together. So if you look here, we have high school A. They rented and filled 8 vans and 8 buses with 240 students total. Then if we look here at high school B, they rented and filled 4 vans and 1 bus with 54 students total. Now this sentence is the sentence that is a comma away from making this word problem clear. Every van had the same number of students in it as did the buses. To me, that reads as it is written that the vans and the buses had the same number of students. Given the setup on this problem, it's not possible for the vans and the buses to have the exact same number of students in them. So a van can have 8 and a bus have 8 students. All right. What I'm pretty sure they're trying to say is every van had the same number of students in it, comma, as did the buses. So the vans, each van to each other van had the same number of students in it, and each bus to each other bus had the same number of students in it. So that comma does make a difference there. And that scenario is why most of you don't like word problems, I'm sure. Sometimes they are needlessly ambiguous, and then we're stuck on that task with that ambiguous word problem. So from here, with that yellow sentence modified with that comma, we can set up our system. All right. High school A rented 8 vans, where X equals the number of students in each van, and 8 buses, where Y equals the number of students in each bus. And if we find the total number of students on buses and add that to the total number of students in all the vans, that will give us the total number of students that went on the field trip overall, which is 240. We are going to replicate that exact same process with high school B. So in this case, we have 4 vans containing X students, and in mathematics means addition, 1 bus with Y students. And if we find that sum, we will find that the total will be 54. All right, from here, we're going to use the elimination method. But if you'll notice, we don't have that opposite sign coefficient lining up here for our x's or our y's. In this case, I'm going to choose to use a multiplier. I see that high school B, if I were to multiply 4 by 2, I get 8. And if I were to multiply 4 by -2, I get -8. Opposite sign coefficient. And so in equations, much like with fractions, what we do to one side, for as long as we do the exact same thing to the other side, then we retain the original value of the equation. In other words, we don't change its meaning. It's like an equivalent fraction. It's literally an equivalent equation. But we have to be careful and make sure we multiply every single term on both sides of the equation by -2 in order for that original value to be retained. In this case, we are going to find that -4 times -2 is -8x. And -2 times 1 is -2y. And 54 times -2 is -108. So I'm going to bring the first equation over. And now this is our new system using equivalent equations. When we are dealing with the elimination method, the goal is to add or subtract. That's why I get the opposite coefficient, so I don't have to worry about subtracting. Subtracting is built in with the opposite coefficient. And we're going to add. In this case, our 8x minus 8x combine as like terms, and they eliminate because 8 minus 8 is 0, and 0 times x is 0, and 0 added on to anything else is not going to change the value. So that goes away. Then we have 8y minus 2y, and that is 6y. And then 240 minus 108 is 132. All right, now we have a single step equation where we are going to do the opposite operation of how the number is attached to the variable. That's attached by multiplication. That is 6 times y. We are going to divide the 6 off from both sides, leaving us with y equal to 22. If you were one of my students at this point, I'd be asking you, have we finished this problem? And it'd be a leading question because the answer is no. We found our y, but we need to find our x. In this case, I actually like high school B's equation better than high school A's. And so I am going to use the original equation here in order to substitute y back in to find the x that would go with this y, and actually both equations. And so that's why you can choose either, because we are finding the point at which these equations intersect on a graph. And so the same x and y value will be found either way. And so I'm bringing down high school B's equation, putting it right there. We are going to take y equals to 22, and we are going to stick that 22 right here for y. Now we have 4x plus 1y. You can write the 1, you don't have to. 1 times whatever we multiply it by is going to be that number. So 1 times 2, 1 times 22 is 22. From here, we have a two-step equation now. But that's okay. We can do the opposite operation of how the numbers are attached to the variable. And since we are doing the opposite operation, we do opposite PEMDAS as well. So that means we are going to undo addition and subtraction first. What we do to one side, for as long as we do the exact same thing to the other side of the equation, we do not change the original value. So we get 4x equal to 54 minus 22, which is 32. We are almost done. 4 is attached to that x by multiplication. Opposite of multiplication is division. Divide each side by 4. What we do to one side, we can do to the other. And we are left with x equal to 8. Now, normally, because we are dealing with a linear system, this would be an ordered pair, and it's still an intersection on the graphs, but we are dealing with a word problem here. So what did we just find? Well, we found that x, we let x equal the number of students in each van. So 8 is the number of students in each van. And we let y equal the number of students in each bus, and y was equal to 22 here. So there's 22 is the number of students in each bus. At the and that is our solution. And just to tie it back to the very beginning, remember how I said this word problem was one comma away from making sense? Well, let's look. If they had really meant that the same number of students in vans as buses, then this wouldn't make any sense because our answer 22 does not equal 8 there. But if they're saying each van has the same number of students in it compared to all the other vans, and each bus has the same number of students compared to all the other buses, then our answer does make sense with that comma. All right, and there you have it. A much lengthier explanation than I had planned, but I wanted to make sure it was clear. If you follow this from top to bottom, you should be able to recognize these pesky word problems that might be ambiguous. And, in this situation, if I was a student, I would have raised my hand and asked my teacher for clarification, even if it was a standardized test, and pointed it out, because sometimes those standardized tests have bad problems too. Thank you so much for your time.